This data. One thing that I do want to draw your attention to when we talk about the downsides of threading from a computational perspective is, from the way I described it to you, each thread controls the interpreter for its unit of time and is the only thing that can run bytecode, which means if I were to write a very naive program that looked like this, and I'm just going to sleep, I'll time this, so from my utils library, import timed. And what I'll do is I'll start a pool of threads. Maybe we'll start 3 of them. We'll go through each element in this pool. We'll start it up. And we'll join these together. We'll define our target. And our target will just sleep for 1 second. Naively, you might think that this thing would take 3 seconds to run. Util. Because that sleep can only run in one unit of computation, can only run the bytecode at once, but you can see this actually takes 1 total second. And irrespective of the number of threads we create, this will only take 1 total second. Deep within the Python standard library, all the way at the C level, certain C calls will release the global interpreter lock. It is not the case that deep computational C code is required to hold on to the global interpreter lock for the duration of its run. And so here, something as simple as time.sleep will actually transparently behind the scenes release the global interpreter lock, as will many other operations that involve waiting, like opening a socket or connecting to a remote resource or SSHing into a remote machine or maybe doing the TCP handshake or checking authorized keys if that's implemented at the C level. If it's implemented at the Python level, well, there's no way for us to release the global interpreter lock at the pure Python level. And to show an example of this where the global interpreter lock is not released, what we'd actually have to do is drop down to the C level. Now, the way we can do that is by going into Python and making use of the actual raw C level sleep. So here we'll get this from our unistandard library. I think it's an unsigned int sleep that takes a number of seconds like this. And here we'll call this, this is no-gil sleep. And here we'll call this C sleep here. Like that. Okay, that should be good. Of course, we need to build our Python library. And if we go back to our code, and here we import, let's get this from our util library. From our C util library, let's import no-gil sleep. Or this is actually our global interpreter lock sleep, so we'll make sure we title that correctly. And I'll even show you another version of this where we explicitly at the Python level release the global interpreter lock. I believe it's written like that. Let me just double check. This is, maybe it's like this. So I have to quickly remember this is, I think it's, I have to pull this from Python. I think I have to go say from Python import no-gil. So I think that's how you write it. And then let me just double check one more thing. That's good. That's good. And this actually, I don't think we can actually release the GIL. I don't think we can actually release the GIL ourselves. We have to do a little bit more mechanics. So I'll just show you the global interpreter lock sleep. If I were to switch this out, then what we would anticipate seeing is this thing will take actually here, and we'll reduce our total number of threads. This thing will now hold the global interpreter lock, and this thing should actually take 3 seconds. So bear in mind that one of the things that we can do with threaded code is if we are trying to do some hardcore number crunching and we have access to the C level, we can actually, using tools like Python, release the global interpreter lock and do a little bit of work. It's somewhat narrow what we're able to do within that within the confines of those restrictions, but it's not the case that we're completely beholden to the GIL in all circumstances. With that said, why don't we go to our program and see if we can apply what we know about threading to this to improve this program. And again, I think it is this place here with the status where we can see some immediate results. We can see some immediate improvement. So what I'm going to do is I'm going to go into my threading module, and I'm going to import thread. There are generally a couple of different ways that we can interact with threads in Python. One of the ways that I prefer is maybe because I like to have very full control over when those threads start and when they stop and how many threads they are. We can create this thread object, giving it a Python function as its target. We can create this in just a loop. So here this is like a pool. We can tell each thing in this pool to start up. Note that if we run this code, the program will terminate with some of these threads still running. So what we can do is we can wait for these threads to all complete. We can join at the end. So of course, if I had a randomness, some random sleep in here, like that, and I didn't do that join, it could be the case that some of these threads are still running when the program terminates, but that join will force this thread to complete before this line will finish executing. So here, something like this. Now, this is one way that I can interact with threads. Another way, and maybe a way, especially if we want to explore both threads and multiprocessing, is to use the concurrent.futures module. And the concurrent.futures module gives us a way to interact with parallel tasks without having to worry about some of these nitty-gritty mechanics of starting and joining these things, without having to worry about how work is allocated to them, and without having to worry about how we move data around. Note that if I wanted to move data around between these targets, like in a producer-consumer, then I'd have to create some global variable, or I have to pass some local variable. I'd have to make sure it's thread safe. I'd have to make sure that we're passing the data back and forth, and that might be a little bit clumsy. So another interface to my threading could be to go into concurrent.futures, import thread pool executor, and to create a thread pool executor with a number of workers, let's say 3 workers, and to submit to it some jobs that I want to run. So here, I'll just still have my target. I'll give this just a sleep for a random amount of time. Let's actually do something like this. Let's sleep for up to 1/10 of a second. Actually, do it like that. And let's also print out the name of this thing, so we just know that this thing ran. So here, we'll get this going. Very good. We have our target, and what we'll do is we'll submit to it our jobs. So actually, I'll submit just one of these first. And here I'll give it a keyword argument of name equals test. Very good. And you can see that ran once. Now, if I want to do multiple tasks, I can do an executor.map. And I can map a function with multiple arguments. So here, we can do something like this. This is worker number X for X in, say, range 10. So we'll do 10 units of work, and it'll map. And you can see there were 3 workers that ran. This is actually, I should say, this is really job number whatever. And if we dug around, we could figure out the thread ID. But here you can see it's automatically identifying that there's going to be 3 workers. It's going to distribute these tasks to all those workers. And nicely enough, it'll collect the results for us. So we don't have to worry about passing data back and forth. And I think this ends up being very close to what we might want to do for at least one of the batches of what we have. Here you can see there are results. Let's actually return a result here. Maybe we'll return a true or false value. We'll take out this here, and we'll actually get our values back. So here we'll take this generator and we'll concretize it to get the result values back. And we should get a bunch of true false values for each one of the 10 jobs. There we go. So I think that's actually pretty close to what we want for this example. And we'll see this actually will work out quite nicely. So from concurrent.futures, we'll import thread pool executor or executor, depending on whether you're an estate lawyer or not. And it's this block that we're going to want to put into that thread pool executor. So we'll comment out this block with our thread pool executor. We'll say, let's try maybe 5 workers. And we want a retrieval job, so we'll do something like get status. This will need a parameter, so that'll be a URL. So that's what we're going to use for the URL. In this, we're not going to have to reach for something like HTTPX. We can just use regular requests. So we'll really take this block that we had before, almost identical to what it looked like before, except here we'll just parameterize this. And instead of adding this to some structure, we'll return it. If it's not a successful job, we'll just return none. And we'll just do something like this. We'll say executor.map, get status. And then here we give it all of the iterables of things that we pass in. We give it all the arguments that we want. So here you can see it's an iterable with all the arguments that we're going to pass into this. So here we're going to pass in URL that looks like this with the actual URL. And this is for URL in completed jobs. That should give us that. We'll get the results. And here we can say results equals filtering these down to the ones that were actually successful. Very good. And I guess this isn't results. This is succeeded jobs. And I'm going to be a little bit more careful because we talk about the job results later. So succeeded jobs. Probably should be successful jobs, but whatever the case may be. And here we'll put an exit after this so we can just see what that does. So I'll show you a little trick. Let's import exit, import sys. We'll set our breakpoint hook equal to exit. This is one of my cute little tricks I like, and I'll put a breakpoint here. And of course, if I wanted to really do a breakpoint, I could do something. I could swap out what that breakpoint hook is. Finally, I think this needs to be name. And I think we are almost there. No connection adapters for that. Okay, why not? That's good. Let's check to see what we did wrong here. That's all fine. This is in requests, so it doesn't like our URL. Our root URL we have. Let's just take a look at what this URL looks like. Let's just make sure that we have some good URLs here. Oh, and of course, this is the first keyword argument. So here we just do like that. Oh, this is first positional argument rather. Okay, very good. So here we go. And 0.7 seconds. Hold on a second. If we don't do this, if we set this to max workers 1, which will more or less be like what the original program looked like, we see that we get slightly over 3 seconds. So actually, it's not bad at all. And what we might think is we might say, if 5 workers can do the work much faster, maybe 30 can do the work even faster. 0.4 seconds, even better. Maybe 300 workers can do the work even faster. Well, it is the case that there are diminishing returns. And in fact, the complexity of interacting between all of the computational units in a threading or async IO or multiprocessing program does lead us to a firm conclusion that it's not the case that just adding the number of additional workers will speed up your code. There's something called Amdahl's law, which will give you some notion of where the breakdown is between more computational units will give you this speed up, or at some point, you may actually find that even more computational units will lead to a slowdown. Thread pool executor is actually kind of smart. If I did this with the just threading.thread approach, I might more visibly see that I'm creating way too many threads and I have so much overhead of creating these threads. Here, the thread collector is actually smart enough to know not to create more threads than it needs to. So in fact, even though I said max workers equals 300, my anticipation is there's probably one worker per URL, and I'm not yet reaching that limit of all the overhead of creating these threads is actually going to slow me down. But whatever the case is, there's a little bit of toggling, a little bit of searching through that parameter space of what the appropriate number of workers are. Bear in mind, in the case of an actual API, I might need to reduce the number of workers to avoid getting rate limited. Because as we know, there are many APIs out there that are even considering beginning to charge for access, and they are very sensitive to people hammering them and perhaps even taking down their API servers. Whatever the case may be, I think what we can see here is threading was actually quite successful at solving the slowness of this code. We took part of this code that was 3 seconds and made it 0.54 seconds.